In lesson 3, we're going to look at applications of exponential functions. So there's going to be some different types, and the first is just looking at our generic exponential functions. So if you remember, we have the growth function, and then we have the decay function. So typically when we're thinking about exponential functions, it's in the form y equals a times b to the x. And a is going to be the initial value, and b is the rate that which your function's growing. So if b is greater than 1, it's growing. If it's between 0 and 1, it's going to be a decay function. So analyzing that a little bit further, you come up with the growth formula to be y equals a times 1 plus r to the x. So basically what I did was I changed the growth rate because when we're looking at b is really the growth factor. So if it's doubling, you would put a 2 in there. Where if you wanted to represent it as a percent, so let's say the function's growing 50%, you would be using this equation here with the 1 plus whatever the percent is as a decimal raised to the x. So whenever you see a percent, you're going to be using this growth formula, where this is going to be when b is a factor. So like if it says it's doubling or it's getting half the size, something like that, where these are going to be used for percents. So the decay version of this is going to be y equals a times 1 minus r because it's decaying. So overall, in the end, 1 plus r and 1 minus r end up becoming the growth or decay factor. Because if I take the percent and I add, so let's say it's 50%, I turn it to a decimal, I add 1 to it, I get 1.5. So now the growth factor is bigger than 1. So that's why it's an exponential growth. Where if I take the 50% and I subtract it from 1, I have 1 minus 0.5, which gives me 0.5. So now my growth factor is a fraction, which tells me that it's not really growing, it's actually decaying, because now it's between 0 and 1. So this stuff in parentheses ends up being the factor, but really the whole reason why I give you these formulas is because when you see these application problems, they typically use percents for growth or decay. But just keep in mind that if it says something about doubling or tripling or getting half the size or a third of the size, that's telling you the factor, and you would just use this original equation here that we already have. So again, a is always going to be the initial amount for both of these. So a is going to be the initial. And then r is the rate. And it's a percent turned into a decimal. So the percent goes to a decimal and then you plug it in. And then x is going to be the time. The time, so like the number of years that this object is growing or decaying, or the number of months, depending on the situation. So let's go ahead and look at some examples that will be using this. So in 1990, the cost of tuition at a state university was $4,300. During the next 3 years, the tuition rose 4% each year. Write an exponential model that gives us the tuition y after t years after 1990. So basically, we know that it says it rose 4%, so this tells me it's a growth function. So I know my equation is going to be y equals a times 1 plus r. And instead of x, I'm going to put t just because it says after t years. So I'm going to go ahead and make that a t. And now what we're going to do is we're going to plug in. So we have y equals the initial amount. So 4,300 is the initial. That's how much it started off with. 1 plus the percentage of growth is 4%, but if you think about 4% as a decimal, it's going to be 0.04. Basically move the decimal places 2 over to the left, or just divide it by 100. And then t we're just going to keep as is because we don't know how many years. So then what I'm going to do is I'm going to go ahead and I'm going to just simplify the part inside of the parentheses. So my equation is going to be 4,300 times 1.04 to the t. So that's the equation. That's the first part. Keep in mind you can't combine these because this 1.04 belongs with the t and the 4,300 doesn't, so you have to keep them separate. And then if you look, it says, so then the second part, what will the tuition be in 2003? So basically, how many years have passed from 2003 after 1990? So if you subtract those, that tells us that we have 13 years between there. So my time is going to be 13. And it's because it says in 1990 is when we're starting, so that's why I'm subtracting 1990 from it. So I go ahead and I use my equation. And I'm going to just plug in the 13. And then we simplify that. So you would just put that into a calculator and you get a number, 7,159. And when you round it, because we're talking about money, I'm going to round 2 decimal places. So the tuition is going to actually end up being $7,159.82. So let's look at another example. So there are 40,000 homes in a neighboring community. Each year, 10% of the homes are expected to stop using their septic systems and connect to the public sewer system. Write an exponential model to represent this data. So 10% are going to stop, which means it's going to decrease. So this is going to be a decay model because now we're losing homes. So we're losing the amount of homes using septic systems. So we know my decay function, y equals a times 1 minus r to the x. And it says there's initially 40,000 homes. So y equals 40,000. 1 minus 10%, so 0.10 to the x. So we're writing an exponential model, so that's why my answer should have a variable left in it. So my answer to this is just going to be the equation. So I have my initial, and then times 1 minus 0.10 is going to give me 0.9 raised to the x. So there's my equation for this. And now it's asking me to find how many homes will be using septic systems in 6 years. So use your equation and plug in for 6. So we have 21,257.64 is the number of homes. So basically how to interpret this is we can't have 0.64 homes. But if you're thinking about the graph of this, since this is a decay function, after 6 years, so let's say after 6 years, we have 21,257.64 homes are left. So really, I can't say that I only have 21,257 homes left because that would be after 6. So I haven't quite decreased enough to round down here. I actually have to end up rounding up. I have to say that there's 21,258 homes that still have the system because I can't count this 0.64 as an additional home. So basically, since it's a decay model, what that means is we're going to round up. So no matter what. So it doesn't, like in this particular one, this 0.6 definitely makes the 7 go up. But that's not really why I'm rounding up. It's because it's a decay model. which tells me that I can't quite say, because if you're looking at, let's say, this point, this is the 21,257.64. I can't um, round down and say that I'm at the lower number yet because you're gradually getting to 6, coming from higher numbers down to smaller numbers. So you're still, like, if you were to describe this, you still have to go with the higher number. So the answer to this is there's 21,258 homes that will be using the septic system still. Because we're not quite at dropping at one home yet. We can't just get rid of that. We can't count 0.64 as a whole entire house. All right, so let's look at another example. So in 1980, about 2,180,000 U.S. workers worked from home. During the next 10 years, the number of workers working from home increased by 5%. So increase tells me it's going to be a growth problem. Write a model giving the number W of workers working from home T years after 1980. So we have our growth model. So y equals a times 1 plus r to the x. I'm going to change my y to represent the situation. So write a model giving the number w, which is really like our y. So I have my initial amount, 2,180,000. 1 plus 5% increase, so 0.05 when you move the decimal 2 places to the left. And then I'm going to use t as my variable. And the first part here again is just writing the equation. So I'm just going to combine those. So here's my equation. And then for the next part, it's asking me how many workers were working from home in 1992. So remember, T represents the number of years after 1980. So you're going to do 1992 minus 1980, which tells me 12 years. So now you're going to use that and you're going to plug that into your model. So we have 12 going in for T in the previous equation. So we have 3,914,966.791, and it's workers. So it doesn't make sense to say that you have 0.791 of a worker. But since this is grow, so if you think about this one on the graph, you're gradually increasing. So if I'm looking at after 12 years, so let's say this is after 12 years, if I'm growing, in order for this to actually work, you can't say that I can't round this up because even though this is a 7, it would push this up to the 6 up to a 7. I can't actually round up because if you look, that would mean that I'm taking my data and I'm saying that after 12 years, you actually get that remainder, that 0.3 of a worker left. You get that remaining piece to get an additional worker. So I can't use the actual y value with the decimal. I have to bump it down and say, really, I only know that by year 12 that there's 3,914,966 workers. So that's as much as you can say. You can't add that additional worker because that would be going past 12. And we only know after 12 years since there's a decimal. So when you answer this, you would have to say 3,914,966 workers. So I didn't round up because of the fact that my equation is growing, so it's not quite up to that next worker, so I can't round up. So basically the rule of thumb here is when it's growth, you have to round your answers down even if the rounding directions wouldn't, like typical rounding directions don't work. So you have to consider the situation. You can't just use typical rounding directions for these because, if it's something that would have to be a whole number, you have to think about it. Well, I'm not quite at that next whole number, so I have to round down because that's what I can guarantee at 12 years. So the next type of formula that we're going to look at is the compound interest formula. So again, it's a type of exponential growth. If we're talking about interest, it should be growing. So this is just a specific type. So just like the other one, we have like some equation, y equals p is the initial. So we put p in when we're talking about money because typically we call that the principal. So this is the principal when we're talking about money. Um, and then this part here is going to calculate to give you that, that growth factor. Notice that we divide r by n this time because n is going to represent the number of times that we compound the interest. So the number of times that we put it together, basically. So we have to divide that rate by the number of times that we're compounding it. And then raised to the nt is, again, we have to multiply the number of times we compound the interest by however many years we're talking about. So looking at this situation, we have Julie invests $6,200 in a savings account earning 3.2% interest compounded monthly. Tells me that I'm going to be using this formula. So the fact that it says compounded monthly tells me I need to use this formula. How much will be in her account after 5 years, assuming she makes no deposits or withdrawals? So we'll start with our formula. A equals P times 1 plus R over N to the NT. And we know that the principal, or the starting amount, is $6,200. And then the R is going to be 0.032 because we're moving the decimal 2 places to the left. N is going to be compounded monthly. So the number of times compounded per year is going to be 12 if you do it every month. So basically when we say compound interest, we're talking about interest on top of interest. So when it's compounding monthly, it's doing that percentage of your entire amount, and then it's adding that interest to the amount. So instead of just using the principal to find the interest, it's actually using the entire account value, take the interest of that, so take 3.2% of that amount, and then add it to it. And then it's doing that every month, which is why we're saying it's being compounded monthly. So then the other part up here is going to be 12 times t. T is going to be 5 years. And then for this, you would just enter this into a calculator to get the actual number they give you. So we would get $7,274.22. So for money, we just round it as normal because we're talking about money. So you're just going to round 2 decimal places. Don't worry about getting whole numbers because we're not talking about people this time. And that's really all it is. It's just plugging in numbers into these formulas. So number 2, we're talking about Tommy's depositing $2,250 in a savings account, earning 1.8% interest compounded quarterly. So this tells me that N equals 4. It's happening every quarter. And how much will he have after 7 years, assuming he makes no deposits or withdrawals? So we have our formula again. A equals P times 1. So 1 plus R over N, all raised to the NT, just like the other problem. So we put our principal in, the original amount. Our rate is going to be 0.018. Move the decimal 2 places to the left. N is going to be 4. It's compounded 4 times a year. And then T is 7. Calculate that, and that'll tell you how much money is left or is now in the account. So you should get $2,551.41. So really, it's just using a formula that deals with money to figure out the interest, the compound interest. The next one here we have Rachel, who's depositing $18,460 in a CD, which earns 4.7% interest compounded semi-annually. So this means twice a year. So N equals 2. How much will she have when the CD expires in 3 years? So the time is going to be 3. The rate is going to be 0.047. We're moving that decimal over 2 places. And the initial is going to be the 18,000. So again, write your formula. So we have the principal, 1 plus 0.047 over n, 2 to the t, which t is 3. Put that in a calculator, and you should get $21,220.65. So that's the amount that Rachel will now have in her account based on the growth. And then one last example here is really looking at the same idea. We're just going to be solving for something different. So it talks about we have $1,000 in an account that's doubling after 4 years. So if it doubles, the account value is now $2,000 after 4 years. What is the interest rate compounded quarterly? So this time we're trying to find R, which is different. Before you're trying to find the amount of money. So now you're actually trying to figure out, well, what interest rate would I have to get so that it's compounded quarterly, and basically so I can double my money after 4 years. So compounded quarterly means n equals 4. So we go ahead and we set this up. So let me just rewrite our formula here. So the amount is going to end up being 2,000. The original is 1,000. 1 plus your interest rate is what you're trying to find. N is going to be 4. And then up here it's going to be 4 times 4 years. And then we just start simplifying some stuff. So I have 2,000 equals 1,000. 1 plus R over 4 to the 16. Divide everything by 1,000 because I'm trying to simplify this. So I got to work to get R by itself, basically. So we get 2 equals 1 plus R over 4 to the 16. So I have to get R by itself. So what I'm going to do is I'm going to take the 16th root of each of these. Because remember, to undo something that's been squared, you take the square root. To undo something that's been raised to the 16th power, you take the 16th root. So I'm going to just leave this as the 16th root of 2 for right now, and then I'll put it all in my calculator. And I get 1 plus R over 4. So then what we can do is we can subtract 1 from both sides. And then we can multiply everything by 4 to get rid of that denominator. So r is going to be 4 times the 16th root of 2 minus 1. And then what we would do is just put this in a calculator and get a value for r. So let's go ahead and do that, and we get 0.177095127 is what you should get out. So that tells me the rate is actually about 17.7% in order to be able to double their money in after 4 years. So then there's one other type of formula here is whenever you have compound interest continuously. So that just means it keeps compounding. So instead of a certain amount of times, it's just going to keep compounding. And in order to represent that with a number, instead of using this 1 plus r over n to the n times t, basically what we do here is we can use e, because as n gets bigger and bigger towards infinity in this situation where 1 plus 1 over n all raised to the n, as n gets bigger and bigger and bigger, what's going to happen is this whole thing approaches the number e. So instead of using this when we keep constantly compound the interest, because remember n represents the number of times you compound per year, so if that number is getting bigger and bigger and bigger, this really ends up almost equaling e, is what we're saying. So we can use e as our approximation. So whenever it says compound continuously, you're going to use this formula. If it says compound in a specific number of times, then you're going to use the one where you have the rate over n. And then if it's just a generic formula where you have growth or decay by a certain percent, you're going to use those original formulas. So there's basically 3 sets of formulas to consider. So looking at this example here, so we have our amount, we have our principal, and then we have the rate and we have the time, and e is just going to stay in there. That's going to be what we're using mathematically to represent this, the number of times being compounded as something continuously happening. So we're only going to be replacing p, r, and t. So looking at this, we have Sean deposits $5,200 into a savings account, earning 1.8% interest compounded continuously. So as soon as you see that, you want to be thinking it's A equals P times E to the RT. So it's the PERT formula, basically, if you look at the way that the letters spell out. So how much money will he have after 8 years? So the amount is going to be the principal times E raised to the rate, which if we move that decimal over 2 places to the left, and then times the time. Well, in this case, 8 years. So you would put that into a calculator as you see it here. The amount is going to be $6,005.40. So let's just look at a couple others of these. Or I guess that's it. I was thinking I had more. So, again, so to summarize then, basically you have your different formulas and when to use what. If you see the words compounding continuously, it's this formula here. You're just simply plugging in. If it's compound interest over a certain specific time over a given year, so like annually, 1 time a year, biannually, twice a year. You could see things like monthly, 12 times a year, quarterly, 4 times a year. Then you're going to be using the formula with the 1 plus r over n raised to the nt. Otherwise, if it's just growing or decaying by a certain percent, you use our common decay and growth formulas. So these formulas here. Or the last scenario is, well, if it just says that I have something that's doubling or getting half as big, it's talking about the factor, you basically just use the growth or decay formula, but instead of doing 1 plus that factor or 1 minus the factor, you just use the factor. So it's just the b. So those are all the different scenarios. Typically when it's talking about money, you're going to be using either this compound interest formula or the compound interest, the compounded continuously interest formula.